Ladies and gentlemen, can I have your attention, please? The 7th International Distinguished Scholar Webinar Series, World Class University, Universitas Pendidikan Indonesia is commencing shortly. I would like everybody to be reminded to keep their microphone off. Thank you. Assalamualaikum warahmatullahi wabarakatuh. A very good morning from Bandung, Indonesia. A very good afternoon or a very good evening to those of you from different sides of the world. It's me again, Chef Ubad Abdullah, and I'm so delighted to be hosting today's event. The Honorable Vice Rector of UPI for Education and Student Affairs, Professor Dr. Didi Sukyadi, the Honorable Director of Directorate of International Affairs, Universitas Pendidikan Indonesia, Bapak Ahmad Bukhari Muslim, PhD, the Honorable today's speaker, Professor David Treagust from School of Education, Curtin University, Australia, the Honorable Moderator, Professor Dr. Phil Ari Widodo, MED, from Science Education Study Program, Universitas Pendidikan Indonesia, the Honorable Deans, Vice Deans, Heads of Departments, Heads of Study Programs, Directors of Directorates, Directors of UPI Regional Campuses, and distinguished guests, ladies and gentlemen. Warmest greetings and welcome to the 7th International Distinguished Scholar Webinar Series, World Class University, Universitas Pendidikan Indonesia. Today's webinar is the 7th out of 7 webinar series organized by Directorate of International Affairs, Universitas Pendidikan Indonesia, as a part of commemoration of UPI's 67th anniversary or Dies Natalis. Today's topic of discussion will be on multi-representation in science education. To begin with, I'd like to invite the Director of Directorate of International Affairs, Universitas Pendidikan Indonesia, DIA UPI, Bapak Ahmad Bukhari Muslim, PhD, to deliver his report. Bapak Ahmad Bukhari, please.
Thank you, MC Pak Ubad. Good morning in Indonesia and other ASEAN countries. Good afternoon, Professor David Treagust in Australia, and good evening for audience in other parts of the world. Honorable Professor Didi Sukyadi, the Vice Rector for Education and Student Affairs, Universitas Pendidikan Indonesia. Honorable Speaker, Professor David Treagust, School of Education, Curtin University, Australia. Honorable Moderator, Professor Ari Widodo, Department of Science Education, Universitas Pendidikan Indonesia. Dear all audience from Indonesia and overseas countries. Assalamualaikum warahmatullahi wabarakatuh. Again, it's with great pleasure to welcome you all virtually to the International Distinguished Scholar Webinar Series 7. This webinar series is organized by Directorate of International Affairs in commemoration with the 67th anniversary or Dies Natalis, Universitas Pendidikan Indonesia. Kindly be advised that this is our final sessions of 7 webinar series organized in October and November 2021. The topic of today's webinar series is Multiple Representation in Science Education by Professor David Treagust, School of Education, Curtin University, Australia. These sessions will be moderated by Professor Ari Widodo of Universitas Pendidikan Indonesia. Ladies and gentlemen, the topic of our webinar today is very timely when students and educators across the world are struggling to navigate notable and huge learning loss due to COVID-19 pandemic-caused learning activities. Despite its benefits, online learning has created students' boredom and cannot compensate the existence of teachers. To rejuvenate students' learning motivations, educators need to expose students to both internal and external representations of learning, particularly in this case is science education. we need to present science concepts in multiple models of representations, such as text, diagrams, analogies, models, equations, mathematical relationship, and computer simulations, as well as different representations such as the macro, submicro, and symbolic levels. This multiple representation is expected to effectively and efficiently address and accommodate the multiple intelligences that our students may have developed in learning. Given the importance of understanding multiple representations among students, particularly in science education, to achieve sustainable development goals in quality education, which Professor David Treagust will discuss in more detail soon, it is no wonder that this webinar has received a significant reception from audience of scholars, researchers, lecturers, and students in Indonesia and overseas. At the moment, we have received about 500 registration of participants coming from across Indonesia and overseas countries such as Brunei, China, Malaysia, Philippines, Ghana, and India. This event is aired via Zoom and TV UV live streaming. Ladies and gentlemen, the organization of this International Distinguished Scholar Webinar Series will not be possible without strong support and resilience of people who have worked very hard behind the scene. These people are staff members of Directorate of International Affairs, Information and Technology, and Public Relations of Universitas Pendidikan Indonesia, who really deserve a big and round applause. Finally, I would like to invite Professor Didi Sukyadi, the Vice Rector for Education and Student Affairs of Universitas Pendidikan Indonesia, to officially open the webinar. Ladies and gentlemen, finally, I wish you a reflective and insightful webinar. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.
Thank you very much, Pak Ahmad Bukhari Muslim, as the Director of Directorate of International Affairs, for the report. Ladies and gentlemen, now I'd like to call upon Rector of Universitas Pendidikan Indonesia, who in this occasion is represented by the Vice Rector for Education and Student Affairs, Professor Dr. Didi Sukyadi, to deliver his welcoming speech as well as to officially open today's webinar. Professor Didi Sukyadi, the floor is virtually yours.
Thank you, Pak Ubed. Good morning, Indonesia and ASEAN countries, and good afternoon in Australia, and good evening in other parts of the world. Honorable Speaker, Professor David Treagust, School of Education, Curtin University, Australia, the Honorable Moderator, Professor Ari Widodo, from Department of Science Education, Universitas Pendidikan Indonesia, the Honorable Director of International Affairs, Bapak Ahmad Bukhari Muslim, PhD. They are all ladies and gentlemen from Indonesia and overseas countries. Assalamualaikum warahmatullahi wabarakatuh. I'm extremely honored to say a few words as the opening of this international webinar series 7. As you may have been informed, this webinar today is the last of 7 webinar series organized by the Directorate of International Affairs as part of 67th UP anniversary or this Natalis. Ladies and gentlemen, effective and empowering learning necessitates teachers, lecturers, and educators to expose students to a comprehensive overview of different models and theories on learning with multiple representation, externally and internally. To engage students in learning science, educators need to enrich their learning experience by the provision of any combination of visible representation, such as pictures, text, graph, and tables. As many scholars, including our esteemed speaker, Professor David Treagust, have indicated in their studies, in order to maintain learners' motivation and accommodate their multiple intelligences, educators need to expose students to the pedagogical practice of such different theories as cognitive theory of multimedia learning, the integrated model of text and picture comprehension, and the depth framework for learning. This multiple representation in science, education, and other subjects or disciplines becomes more necessary during the unprecedented pandemic time in which our students and learners experience a great learning loss due to overexposure to virtual model of learning. In my discipline, I learned a bit about multimodality. So if we want to utter our ideas, we use symbols to represent our ideas. And our objective in using the symbols will be much more fruitful, which be much more effective when we are using not only one mode, but we can use multi-mode ways of representing ideas. We can use parable mode, we can use visual modes, we can also use audio visual mode, such as video. And I know that multimodality studies in language disciplines is mainly based on research in science education, especially in science textbook, because science textbooks use more pictures, more diagram, more tables with quite colorful representation. So we also apply this kind of approach in literacy studies, for example, in using novels or stories for children. Yeah, and my colleagues and I have done a small scale research on this topic. Ladies and gentlemen, I believe that this webinar by Professor David Treagust, with his strong expertise and extensive experience in the area of multiple representation in science education, will open up more discussion on how we educators can involve our students in more engaging learning activities by exposing them to multiple representation for more quality learning. Finally, as requested by Pa Abu and also by Pa Ubad, I would now officially declare that this final webinar series open by saying Basmalah. Bismillahirrahmanirrahim. I wish you a fruitful and insightful webinar. Thank you very much and a very good day to all of you. Assalamualaikum warahmatullahi wabarakatuh.
By Professor David Treagust. But first, allow me to remind you several points as follows. Number one, on the Q&A session, you can drop your questions not on the chat room of the Zoom or on the comment section of the YouTube live streaming on TV UP channel, but you can go to slido.com and you enter the code of hashtag TOPWebinar7. It is case sensitive, so be advised that the TOPW, or in capital letters, and the EBINAR are in the small capital letters, and the 7 is in number. Or you can scan the QR code on your display, and later we will select the question to be asked to the speaker. Number 2, do not forget to fill in the attendance link distributed to either the comment section on the YouTube channel or the chat room on the Zoom meetings, because your certificate will be based on your attendance record there. And don't forget to also subscribe the TVUP YouTube channel to get updates on internationalization and any other programs of Universitas Pendidikan Indonesia. Ladies and gentlemen, this session will be chaired by Professor Dr. Phil Ari Widodo, MED. But first, allow me to introduce his CV briefly. Ari Widodo is a professor and also a lecturer at Science Education Study Program in Universitas Pendidikan Indonesia. He finished his Bachelor in Biology Education program from IKIP Bandung, the former Universitas Pendidikan Indonesia, in 1991. He holds Master of Science Education from Deakin University, Australia, and in 2004 he finished his doctorate degree in the University of Kiel, Germany. His research conducted is mostly related to the learning process, which includes constructivism and conceptual change, reasoning, STEM, and education for sustainable development, or ESD. In addition, he is also interested in research for the professional development of science teachers and pedagogical content knowledge, the so-called PCK. So, ladies and gentlemen, without further ado, please join me in giving the kindest, the warmest welcome to Professor Ari Widodo.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Thank you very much for the very nice introduction. But I believe that the participants joining this webinar not because of me, just because of David Treagust. So without further ado, I would like to introduce our speaker today. He's Professor David Treagust. I'm very honored and very glad to accompany him in this morning. He's a good friend of my supervisor, so he's indirectly my teacher also my supervisor also. So David Treagust is a professor is a distinguished professor at Curtin University in Perth, Western Australia, where he supervises research students on topics related to understanding of students' ideas about science concepts and how these ideas relate to conceptual change and multiple representations, and also on the design of science curricula and teacher classroom practices. David Treagust holds a PhD and MS from the University of Iowa in the US, BSc from the University of Western Australia, and Certificate of Education from Worcester College, University of Birmingham, England. He holds a fellowship in Royal Society of Biology in 2008, the American Educational Research Association in 2010, the Royal Society of Chemistry in 2016, and the Academy of Social Sciences Australia in 2019. So, David Treagust taught high school science and chemistry for 10 years. He is the author of more than 350 publications in major journals and books in science education research and chemical education research, and is a regular contributor to national and international conferences. He is a co-editor of the Springer book series, Multiple Representation in Chemical Education, written together with John Gilbert, Multiple Representation in Biological Education, written together with Chi-Yan Sui, and Multiple Representation in Physics Education with Reinders Dutt and Han Fischer. He has more than 30 years experience in supervising doctoral students in science education, and I believe there are many Indonesian students also supervised by David Treagust, and editors of 4 research journals. He has been the recipient of 15 Australian Research Council grants that have involved working with science teachers in Western Australian science classroom to implement a wide range of interventions to improve students' learning of science concepts across the curriculum. This work has resulted in numerous national and international publications in journals of science education research. His work is well cited with a Google Scholar of Age Index of 94, representing over 35,000 citations. That's a very excellent. So, without further ado, let's us start our webinar this morning. So, give it, please.
Thank you. I've lost the pictures of other people, but you can see me, right? Ari?
Yes, I can see you.
You. Right. You can hear me too.
Yes, very clear.
Very clear. Thank you very much for the invitation in general, and thank you for the invitation by the Vice Rector, the moderator, and Ari for your kind words. Selamat pagi. It's morning here. And I was very impressed with the video. I mean, it tells an interesting story. And this wonderful iconic building, which has been there from the development of the time when Indonesia had IKIPs and moved to universities of education. So thank you. So as everyone has informed you about this talk about multiple representations, I was very interested to know the Vice Rector talking about multiple representations. And so this is clearly an issue of general interest. So what I'd like to do today is talk some very general points about where we are with learning. That's part A. And then I talk about different modes and different representations, which is a little bit more detail. And then more detail still with a case study of learning optics in first year university physics students. So if we go back to Bloom's taxonomy, and you will remember that this began in 1956 and then was revised in 2001, moving more to from nouns to verbs. And one of the things I want to emphasize here is that with multiple representations, it gives us an opportunity to teach in a way and for students to learn in a way that moves higher up that triangle. So this is the important point. We want people to go from understanding to applying to analyzing to evaluating and being creative. If I look at the aims of science curriculum in Australia, ACARA is the Australian Curriculum Council, and I just highlight some points there in blue. So the goal is to provide a solid foundation in science knowledge, understanding, skills, and values, foster interest and curiosity, engage in communication, value evidence, question scientific claims, identify and investigate scientific questions, and draw evidence-based conclusions. It's very difficult to attend to those issues if we do not look at the concepts that we're learning from multiple directions. You cannot memorize and learn things and have only basic knowledge and attend to those questions. Yes?
Sorry, David, to interrupt. Can you please share your screen?
Oh, why am I not doing that?
Thank you.
I thought I was sharing my screen. Oh dear. I've got a problem here, and I need to get some help. I've got to find a technician. Sorry.
On the bottom there's a green screen. Share screen. Then you can.
Is it? Can you see the screen now?
No, not yet.
Oh, all right.
It's not shared yet. Thank you.
Okay. Sorry. I'm not sure what's going on. Because it was showing before. So let's see. Share screen.
So if you see on the Zoom screen, okay.
Can you
Okay.
see my screen now?
Okay.
Do you see my screen?
Yes. 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 It's
Oh,
showing
okay.
now. It's showing now. Thank
So
you.
this is what it looked like before.
Yes.
And then I talked about the
Yeah.
summary of what I'm going to do.
Yes.
So I'll just revisit, talk about background of the talk. I'm going to talk about different issues, and then learning science with different modes and different representations, and then more detail again with a case study.
Okay, please continue, David.
What, you can see me now?
Yes. Yes.
Yeah, good. Okay. So what I was talking about here was, if you look at the aims of the science curriculum, and this will be the same for many countries, this is the one from Australia, to attend to all those issues that are in the curriculum goals, you need to be looking at science from multiple directions, from multiple representations. And then if we look at the complexity of the curriculum, we look at the main points about chemistry, and we don't need to read all those in detail, but you can see that it's made up of main issues, and the main issues are structured in such a way that we know that we take these topics when we're studying. So if we think about what's going on in a lesson, there's many opportunities for learning in a lesson, and this was mentioned already by the moderator and the Vice Chancellor. In a lesson, we're dealing with language. We're talking about talking, we're listening, we're questioning, we're relating ideas, we're looking at text, reading words, we're looking at tables, graphics, drawings, images, photos. And then we've got the actions of laboratory work, which can be of various types. It can be a confirmatory laboratory, or it can be an investigative laboratory. We use computers, and we can use immersive virtual reality. And all of the above are referred to as multiple external representations, or more simply, multiple representations. So the big point is that co-deployment of these multiple representations improves understanding and reasoning. And one of the colleagues, Sharon Ainsworth, has some theoretical model about this, and I can mention this a little bit. So there are many ways that we can learn about science. For teachers to teach and learners to learn, so we can look at these connections with other knowledge by using analogies and using metaphors. We can make connections with what can be seen, such as enhancing visualization, using various discourse patterns, look at models and modeling. And then we can deal with different levels of representations, different modes of representations, and all this comes together as a mental model. And one of the points is we need to differentiate what is real and what is a representation. And the internal representations we refer to as mental models. So some people research on mental models. So I presented this in one of the multiple representation books, I think the one in chemistry. Perhaps every course should begin with showing this painting. The painting is by the Belgian surrealist artist René Magritte, and the translation there from the French, this is not a pipe. This is not a pipe. I've actually seen this painting. It's a very large painting. And when you look at the painting, the immediate response is, this looks like a pipe to me. And then you realize, this is not a pipe. This is a painting of a pipe. It's a representation of a pipe. So to me, this really enhances what we're trying to do when we're talking about different representations in science. And I come back to that later. Connections with other ways of knowing. We've got this work on analogies, and I'm not going to go into any detail about this, but I'm going to refer to this book by Richard Cole and Alan Harrison. Both those colleagues are doctoral graduates of mine. And what we did was develop a way that was more effective for teaching with analogy. Analogy is something that you're familiar with. So for example, you can try and learn about the study of electrons in a circuit by looking at a water model diagram of water flowing through pipes, and a lot of research like that. And then you've got this other book, again with Alan Harrison, Peter Orbison, and Stephen Ritchie, that deals with metaphor and analogy and science education. So I recommend you to read those books. And if you wish to discuss more about analogies and metaphors, we can do that in the question and answer. I mentioned about visualization. John Gilbert, who passed away earlier this year, sadly, he was one of the first academics to emphasize different aspects of visualization, what you can see and how it's brought together for learning. And then with Rosaria Justi, the two of them presented this text on model-based teaching in science education. So it's the idea of using models of different types for teaching. So that's the first part of what I want to do. It's like a background as to where I'm going to go, and now I'm going to present things in a little bit more detail. So in terms of learning science with different modes and different representations, science knowledge is learned in different modes, with words and the way something is expressed. And this can be done in a visual way, by writing, by reading what's written, by using animations, computer animations. We can learn the modes as you're doing now by listening. We can have some discussion and the question and answer. We can also do experiments, and we can do mathematical work too. In many departments, we have not just mathematics in the mathematics department, but you have mathematical modelers in chemistry and physics and the like. They are theoreticians. And each mode has strengths and weaknesses that can help most to communicate the scientific ideas. What about modes of representation? So there are many, again, discussed very nicely by the Vice Rector. So in terms of a continuing of increasing abstraction, in terms of representation, we got real life objects. So you can bring a reptile, for example, into the laboratory and you can observe its behavior. You have actions when you are presenting. You tend to look at, you emphasize different things by different gestures, and that lends itself to a realm of research. You can learn from photographs, you can learn from animations. You can write about what is seen, which is what students do when they do laboratories. You can make drawings and diagrams of events. You collect data and you put this into graphs, into charts, into tables. And if you want to make better sense of how these different variables are related, you can make an equation. And you've got paper-based text and now screen-based text and oral presentations. So I bring this all together into one document. I'm just going to spend a little bit more time on this document. So as was explained by Ari at the very beginning, one of the books that I edited was Multiple Representations in Biology Education with Cheyenne Su. Cheyenne Su was a doctoral student of mine, and he had this idea long ago to write a book when he finished his doctoral thesis. And so we have this introduction to multiple representations, and you can see how this like theoretical model fits together. So if you look at the horizontal translation, some of the issues that I've just been dealing with, modes in a continuation of increasing abstraction, will the objects and actions, photos, animation, natural drawings, maps, diagrams, graphs, tables, equation, linguistic input and output, discussion and interaction. So those different modes are needed to help explain what we're doing, what we're expressing, and we need to have a way to work out what it is we're talking about. So as I'll explain a little bit more later, science is represented at different levels. In this case, we've got macro, which is what you can see, micro, which is maybe what we can see through a microscope, submicro that we cannot see through a microscope, and then we got symbolic representations, which like fits with the equations. And then in terms of this knowledge domain, here for biology, we got evolution, homeostasis, energy, matter, and organization, continuity, development, and ecology. And this is the domains of science, biology arranged by the biological sciences curriculum study. So you can see if you're dealing with, say, evolution or dealing with ecology, you have many ways to represent it. So one realizes just how complicated science is in terms of learning it when you don't know anything. So I'm now going to address these in a little bit more detail. So here's this book edited with John Gilbert. We selected authors who we knew who were working with multiple representations, and I'll explain this as we go along. So in terms of chemistry, I think we're all very well aware there are three levels of dealing with representations. They're what we can see, visible to the naked eye, the bulk properties of matter that we call macroscopic. We've got molecular, which is at the particulate level. It's non-observable to the naked eye, but it's only at the molecular level that things are happening. So we get the changes that are taking place in a reaction. And then the symbolic provides explanatory mechanisms of phenomena represented by symbols formulas, chemical equations, and numerical calculations. But what is the chemistry? Well, here is another way of looking at it. In a LMI flask, we have some water. So you can see that it's a liquid in there. It's represented by H2O, and it's got a certain structure, H2O, by that model. And so you've got a nice little diagram there, how all those fit together. And if we go one step more, if we look at all these representations are combustion of methane, but they're not methane burning. I have a YouTube here, but I'm not sure how to use it in the middle of a talk. I'm sorry about that. But that YouTube shows a person with methane and a candle, and the candle lights the methane, and so the methane you cannot see initially, and then it all flares up. So combustion of methane means we've got methane, CH4, and it burns, and it produces carbon dioxide and water. So we can represent that by equations. We can represent it by models, different types of models. And what we notice is the atoms are rearranged. So this is a big understanding for students learning with representations. Now, without going into the details of the book, but to try and point out the kind of work that we were looking at when we invited colleagues to talk about multiple representations in their work, we had colleagues dealing with structural representations in organic chemistry, better learning from diagrams, better learning using symbolic level. We looked at the role of practical work to emphasize the macro level and to emphasize the macro level with a purpose, not just doing activity. Ways to teach inorganic qualitative analysis, and again, linking macro and submicro level with diagrams. In terms of classroom solutions, we dealt with structure property relations involving meso levels. These are different levels between macro and micro, and then dealing with historical materials, looking for explanations of the macro phenomenon. And you know, this is very interesting material. And then the role of multimedia and how computer simulations can be used. So all those are different representations for learning about chemistry. If we go to biological education, I introduced this paper already, this book with Chien Hsu. So if we look at biology's got 4 levels. We've got macroscopic, which is the biological structures which are visible to the human eye. We've got cellular and subcellular levels, which is are visible under a light microscope. We have molecular submicroscopic, which involve DNA, proteins, various biochemicals that can be identified using electrophoresis or chromatography and the centrifuge, but cannot be seen by the human eye. And then we have symbolic, that provides explanatory mechanisms and phenomena represented by symbols, formulas, chemical equations, metabolic pathways, numerical calculations, genotypes, inheritance patterns, phylogenetic trees, etc. So lots of ways to represent in symbols in biology, and I introduce a few of them. So we're all familiar with this structure of DNA, and this is one of those chapters that dealt with diagrams. The Roth and Pozza Ardengi are two authors in the textbook. You've got a diagrammatic representation of DNA, which those of us in biology are very familiar with. So you see how these bases fit together. We have another example this way of multiple representations of the human respiratory system. So they're all representations from biology textbook. You can see in the middle case, it is the real. It's a picture of the lungs. On the left-hand side, you have a diagram of the lungs. And the diagram is showing the different parts and what they are. They have a name and how they're connected. And then on the right-hand side, you've got how the lungs are working in terms of when we breathe, what are we doing? We've got we're taking in air, we're inspiring and we're expiring, and what's going on during this time. And so we got all the details there in terms of volume in milliliters of air that's going in and out of our lungs. So they're all representations. I think what happens at a younger level, the students draw the diagram. At the more advanced level, they're looking at the the breathing in and out of air. Here's another case of multiple representations. This is a very interesting software which dealt with dragons. Biologica is the name of the material, and you can see here that we have the phenotype. The macro level is the diagram, is the dragon, sorry, and we can see the chromosomes on the that make up the genotype of the dragon, and then we can see how the chromosomes are arranged, and the genes and the DNA molecules and how they are arranged. So what happens with this software, you can take two dragons, a male and female dragon, and have them produce offspring, and then the offspring, you can look at the genotype. So it's a real world event. We've done a lot of studies with this, and one of the things we find is there's a gender difference. The boys love this kind of things. The girls are not so interested. They'd rather be learning about the biology of real people rather than dragons. So that's reported in that chapter there. Here's another paper from Clement and Castira in the same book that looked at environmental influences of genetic diseases and the number of cases and the environmental factors. So this kind of diagram, a chart or whatever you want to call it, gives you lots of useful information. So it's telling us that for people with diabetes, about 55% of them, 55% of people have diabetes, and about half of that number are due to environmental factors. The same with cancers, and then you've got other issues like sickle cell disease, which I think you know is more to do with genetic factors. So again, a different way of representing data, and with the different ways of representing, you learn a lot of information. Again, this book now in some detail, what did we ask people to do? To provide information about external representations in terms of computer simulations. How do they work? Genetics reasoning, and lots of research on that in different fields as well. Using in animations, how do we learn from animations? What about systems thinking? Systems thinking, this work was produced in 2013, and now systems thinking is a very big field. So you find lots of issues to do with systems thinking in the journals. Visualization using analogies, so that's come back to the initial work that I talked about. We have gene-environment interactions. That's the work that I showed you about the different diseases. We got complex biological processes. How do students learn about them? And then we've got learning tree diagram thinking in evolution. And if you look at evolutionary charts, they're not easy to understand unless it's explained to you what this all means. And I come back to that point a little bit later. So the third book is Multiple Representations in Physics Education. Again, we've got the macroscopic, which is what you can observe. We've got the molecular. For example, I chose an example there of gas laws. And then we got symbolic, which is explanatory mechanisms of phenomena. We're using symbols, formulas, equations, we're graphing relations. And often these are idealized situations like a body moving over a surface without any friction. So here's an example of multimedia that you typically find in a textbook. And we don't need to go into detail, but just to point out, to learn effectively, we find that students need to read the text and see the diagram. Most students don't learn best from only the text and don't learn best from only the diagram. They learn better when the two are together. So sometimes if you look at older textbooks, they don't have many pictures or many diagrams. And now more modern textbooks have got many diagrams and many pictures and many photos. And the reason is because people learn better when they can link the two types of representations. One is text, the other is diagram. Here's another very common way of representing that you know. Again, don't need to go into any detail, but you see the point. A man pulls a child in a sled on a constant velocity, and so you've got issues to do with weight and the different forces, and what the student has to do in learning this kind of physics is work out where the forces are and calculate them. In terms of the physics textbook, we looked at models and modeling. In upper secondary school, integrating computers, computational artifacts, using multiple analogies, social semiotics, which is mentioned before about how people behave with their hands and explaining things with movement. We got issues to do with learning optics. I talk a bit about that later in the third part of the talk. Astronomy, using forces like the diagram I showed you, how textbooks represent electric current, sometimes very well and sometimes not so well. Dealing with geometric optics, physics learning, and then trying to link many things together: dynamics, thermal physics, electromagnetic induction, and superposition, and see how all those fit together. And then we got heat transfer, and how you represent that in diagrams, and how we use it in teaching. So all these aspects deal with different representations, different ways of presenting, different modes, and I will deal with one of them in detail later. So learning with multiple representations, examples there. And then if we deal with this notion of Ainsworth, so Ainsworth's argument, and there are two papers I reference here. One went a little bit earlier, and this is another one. So if we're using multiple representations, they've got functions, and the functions are basically to complement each other, and that was mentioned at the very beginning of this talk. They constrain interpretation of a phenomenon. In other words, if I look at the diagrams and I don't really understand what's in the diagram, I read the text, and the text then tells me a little bit more, and then I can understand the diagram. And hopefully, we construct deeper understanding of phenomenon with these multiple representations. So what is the argument? Learning science with different modes and different representations can improve understanding of scientific conceptual knowledge. It can enhance problem-solving skills using different modes. It can reduce difficulties in understanding links between different representations. It can lead to less fragmented knowledge and more coherent understanding. So if you go back to that Bloom taxonomy, the fragmented knowledge often is at a low level. It's at the memorization level, and we can't do much with it. So if we learn to link those different parts of knowledge, we develop a coherent understanding. And the whole idea of different representations and different modes, it helps students to understand science, not to memorize things. However, a lot depends on a test. If we have a test that deals with memorization, then we need to know that needs to be memorized for the test. And hopefully we have other tests that require understanding. The teacher's role is to identify the different types of representations and their use. So don't leave this up to the students. Tell them why we're using, in terms of chemistry, why are we using ball and stick models? Why are we using space-filling models? It's not because we ran out of space-filling models that we use ball and stick models. They each have representations. Each are representations of molecules that tell us something. And the teacher needs to emphasize the significance of the relationship between the representations. So what's the implications for learning with multiple representations? A combination of different representations enables the learner to attend to the subject from different perspectives. And I think this is really important, but it's very demanding also. Learning with different representations provides new insights and construction of new knowledge, and it enables deeper understanding and coherent knowledge, hopefully. And I point out to you in a little while that this isn't always the case. Notions of representational competence vary across contexts and can be context specific. So again, this is a good reason why the teacher needs to identify what the representations are and why we're using them. So when students do not master the ideas of different representational types, they misunderstand the meanings of models and their use, such as stick and space-filling models. They do not see why lab work is useful. Most students enjoy doing labs, but many don't know why they're doing the lab. They just follow the points in the lab. And this experience with macro is very important for understanding what's going on in an experiment. If we don't use different representations, alternative conceptions can develop. We don't understand the complex conventions. We have to learn these conventions, by the way. And you can't move mentally between the types of representations. And as I pointed out, these can be very challenging, and so it needs an effective teacher to bring these to a student's awareness and understanding. Okay, so I just want to just revisit what I've tried to do. I've tried to point out the multiple issues that we have to deal with when dealing with any science. And I just chose physics, chemistry, and biology. Learning science is complicated. It's complex. It's difficult, and we have to learn how to present it in a certain way that makes sense to students. And what I then presented were 3 examples of textbooks with ideas that were presented whereby multiple representations are enhancing learning opportunities. And so the third part and a shorter part of this talk is this case study, learning optics with multiple representations. So this is a real study. Yen-Rui Ko was the leading author. He was a doctoral student on this work. The other people were supervisors of his work. So the research questions were, how well do students use multiple representations in learning optics? And how valid and useful is Ainsworth's framework? That's that framework with the 3 aspects of complement, constrain, or enhance in analyzing the effectiveness of learning with multiple representations. So we had a university introductory physics unit. There were 150 non-major students. The students had low physics knowledge. If they were majors, they'd be in another program. These were typical students that needed a physics unit to continue with some work in another department. A very experienced lecturer, this guy Siddiqui was a lecturer, and he had lots of experience using multiple representations in his lectures. So we documented his lectures, what he was doing, so we knew how the representations were presented, and we knew when the representations were related from one representation to the other. So when this was finished, we had 8-item conceptual tests with open answers, and I show you some examples in a minute. And what the students were asked to do was to answer the question in terms of a text, make some writing, draw a diagram, show the relationship in an equation, and make a graph. So this is how they were taught. They were taught these aspects of optics in terms of text, diagrams, equations, and graphs. And the questions related to everyday life experiences. and the questions were directly related to the course content. So we had these observations, as I mentioned. We observed all classrooms. We had questionnaires, which I show you, and we had student interviews. So the questionnaires were like this, and I need to just read to you in detail here. So this is an example of what we're asking the students to do. So they've got this example as a model to answer the 8 questions that are on their end of semester test. Please explain your answer using words. So we're dealing with if the radius of a concave mirror increases, what will happen to the image? So we've got, please explain your answer in words. We've got the words. Please sketch a diagram and label it. And we've got that. Is there a formula that can help you with your explanation? And how can this formula help you with your explanation? And is there a relationship that you can draw? So they've got this example, and then they're asked to answer other questions. And so the other questions were, this is an example. We say everyday example, but I don't think many people go fishing with a spear. They use a line. So if you're spearing a fish, would you aim above, below, or directly at the fish to make a direct hit? If you zap the fish with a laser beam instead, would you aim above, below, or at the observed fish? So write an explanation, draw a diagram, and support your explanation using a formula and calculations where appropriate. Another example, assume you're standing 1 meter in front of a mirror. Will your image be smaller, same height, or larger than the actual height? Write an explanation, draw a diagram, draw a labeled scale, and support your explanation where appropriate with calculations. So what we found was, remember, the students have been taught in a certain way, and they've been given this example, how they would present their responses in 4 different ways, 4 different representations. Most of the students provided written explanations for the explanations. A similar number of students drew some type of diagrams, but on average, students adopted only 2 of the possible 4 representations. So this was very disappointing. Something's going on with the teaching or with the learning that wasn't anything like as effective as we'd anticipated. With the interviews, we interviewed 69 of the 73 students. They said they gained a better understanding by having these multiple representations, and the majority said it helped them make the connections between representations. So certainly it did this in terms of the oral and the diagram. So what's a summary? Students did not use the multiple representation shown by the lecturer, even though this was overtly demonstrated. And we had looked at other research, and this is consistent with prior research with students with low prior knowledge. So this is a problem that was already within the study design that we hadn't really worked out. If we looked at Ainsworth framework for useful, for determining the extent of learning being complemented, constrained, and more deeply constructed, I think what we found was that there were complementary learning, as I mentioned, with the text and the diagrams. The constraining and the more deeply constructed nature were less in evident. The tutors need a good understanding of the roles of the multiple representations, and we tutored them, but it obviously didn't work so well as we'd anticipated. So concluding comments on this study, the majority of students use more than one multiple representation. So that's a good thing. They did more than describe or draw a diagram, but most did not use their knowledge in a coherent manner. They tended to focus on words and equations, not diagrams and not graphs. This may be what they see is more likely to be emphasized in the physics. Explicit guidance was needed by the tutors. Interviews with the students support the observed lack of presentation of multiple representations in their questionnaires. In other words, when they interviewed, they also didn't add more information. And in terms of Ainsworth's framework, there was some evidence of the different multiple representations being complementary, some evidence of constraining, that if they learn more from one by reviewing the other, but there's limited evidence of students constructing deeper understanding. So a little bit disappointing. Okay, so I come to the conclusion of this talk, and I thank you for listening over such a lengthy period, and I look forward to discussing with you in different issues. So what I've tried to do is discuss the complexity of learning science. I introduced Bloom's taxonomy, the aims of science education, the domains of science and the multiple opportunities for learning science. I illustrated the importance of using multiple representations to learn science. I examined research using multiple representations in chemistry, biology, and physics. I briefly looked at a theoretical framework. I mean, that could have been the study, but I chose not to do that. And I presented a case study that really demonstrated the challenges that we face when teaching with multiple representations. So that's the end of my talk. So Ari, thank you very much.
Thank you, David, for this talk. It's inspiring and as well as thinking provoking for us. So I believe that many Indonesians, many of us, also conducted research on multiple representations.
I'm sure you did.
And we have many questions from our participants this morning. So I'll try to pick up one by one. And hopefully we have the time to respond. Okay.
Should I stop sharing the screen?
Yes, please. Yes, please.
Yeah. Okay. So. Oh, so what's happened now? So here are the questions. Right.
Yes. These are the questions. And maybe we can pick up from the very first question or the second question.
Yeah.
Okay. I think we have further down below. We have started from the first question. Yes. Could you please scroll down?
Oh, many questions. Whoa.
many questions, David. Can we Halim from USK? Is that USK? Where is USK?
Start at the top and just go down.
How to Halim from USK? The question is how to overcome so that there are no misconceptions when we are using analogy strategies in science learning.
Right. So, you're perfectly correct to bring this up because what I did a lot of work on analogies in science classrooms, and what we discovered was that a teacher is teaching something, and then they realize, oh, the students don't understand. Let me think of an analogy. And they present an analogy, and the students have got no idea what the analogy is all about. So what we did with and this book that was introduced, which we call the FAR Guide, which was focus, action, and reflection. We worked out a model with working with about 10 teachers, how to present analogies in a way that had been thought about before the lesson. So in other words, I, as an experienced teacher, know that students can't understand something or they make mistakes. So let me deal with this in terms of what do I want to focus on, what action am I going to make, and how the student's going to reflect on it. So we had this model, we call it a FAR guide, F-A-R, and the idea was that students and the teacher draw parallels between the analogy and the target, and we overtly state what is common and what is not common. So for example, and I'm just thinking off the top of my head, like with this water flowing through pipes analogy for electrons flowing through a wire for electricity, one of the issues is the water actually flows through the pipe. The electrons don't flow through the pipe. They vibrate and move along. So we make sure there are no misconceptions or limited misconceptions by looking at the analogy and identifying what is common with the analogy and the target and what is not common. And in that way, the students tend not to use features of the analogy in an incorrect way and get a misconception. Thank you for the question.
Okay, thank you for the explanation, Sir David. Next, I'm going to pick up a question from a college from Malaysia, University Technology Malaysia, Mas Helena. The question is how to differentiate between translations and transformation between math in learning science and problem solving.
Right. I'm not 100% sure what you mean by translations and transformations. Do you mean that in a translation, a student's making an understanding between say the text and a diagram, and in transformation they are creating say a relationship in an equation form from the text. Is that the kind of thing you're referring to?
I'm not very sure because this is just
Yeah.
context. Yeah. Okay.
Okay.
So let's move to the next
questions.
It's from
From
Udan
Udan
Kusmawan
Kusmawan
from
from
Universitas
Universitas
Terbuka in
Terbuka in
Indonesia.
Indonesia.
The
The
question is,
question is,
how
how
could we
could we
measure
measure
if
if
a
a
representation
representation
accurately
accurately
represents the
represents the
concept of
concept of
science
science
we are
we are
teaching
teaching
and
and
not
not
lead to
lead
a
to a
misconception?
misconception?
Yeah, right. Okay. Yes, I mean this is the essential nature of teaching, isn't it? That students can always develop a misconception. That there's no doubt about that whatsoever. The chances are, if you're using more than one representation, the students get a different way to look at what they are trying to understand, and the chance of having a misconception is much lesser. I think that's the issue. Because a representation, like, for example, if you think about that pipe, the pipe is a representation, but you can't do anything with it if you wanted to smoke tobacco. So it's got every representation's got some limitation. So from my point of view, like with that teaching with analogies, it is good to be overt and say what the representation does not tell us. So for example, with the ball and stick and space filling model for molecules, this actually doesn't tell us about the size of the molecule or what water looks like. And again, I can relate something quite recently with students who were given several ball and stick molecules and asked them to say, how would these be, how would you join them together to represent water? And some students connected the hydrogen to the oxygen, and some just stacked the molecules all on top of one another. So the ones that stack the molecules on top of one another, you realize they don't know what that molecule represents. So I think I think the short answer to that question is you need to be very overt about what the representation is. Okay.
Thank you,
Thank you,
David.
David.
Let's move to the next question. It's from Desi Fajar from
Satya
Satyawacana
Wacana University, Satya
Satyawacana
Wacana Christian University.
The question is, should we consider students' learning style before we implement
learning with multiple representation?
Okay, so it's not on the screen, right? This question.
From Satya Wacana, Desi Fajar.
Where did you say it?
Okay, there's it. So should we consider students' learning style? Yeah.
Oh, right. Okay. That's an interesting question because I'm not sure whether learning style is considered to be as rigorous as we thought it was in the past in terms of research. However, I agree with you that if a student is better to learn orally, then they can engage in a lecture and get a better understanding. Some students are better learning from text. So I think you as a teacher or a lecturer know your students, and you can help them in that way. And one of the issues that's made me realize, these students I mentioned, the physics students who were non-physics majors, who didn't represent their understanding in the way that we anticipated, they probably had a learning style that was not like using equations or using mathematics to express themselves. Yeah. I hope I partly answered that question.
So, thank you. One question quite related to the question that you just answered. Just pop up questions, and it's from VD from UPI.
Yeah.
How can we be sure that the representation we choose is appropriate for the level of student thinking? So the first question was about the learning style, and now whether the question is fit to level of student thinking.
Well, okay. This is your experience of the students.
Mhm.
So obviously, you don't want to have a representation that's overly complicated. If it's overly complicated, the students cannot make sense of the representation. I mean, I've seen some studies where students use cartoons as representation. So if that's a level of the students' thinking, that they learn better from cartoons than they do from the text, then this will be helpful. So I think it's up to you to work out the level of students' understanding and decide what kind of representation can be used. Okay, thank you.
Okay. I'm going to pick up a question. This from anonymous. There's no names here. The question is: students need knowledge to draw or use representations, and at the same time, representation can be used to learn concepts.
Right. Yes. Yes.
Yeah.
Yes.
How is it?
Right. This is perfect. Yeah. This is the essential issue, isn't it? That if they don't have any knowledge, it's hard to make a representation. And this is part of the problem with that case study that I showed you. So students do need knowledge, but have you had the experience where you do not know what it is you're reading, and you read it again and again, and you understand? So you have all these this fragmented knowledge that sometimes doesn't get an opportunity to come together. But if you practice, as it were, this information comes together. So yes, they need knowledge to use the representations, and then once they've got the knowledge, they can use the representation. That's a very good question.
So thank you.
Makes me think a little bit too about this. Right.
Thank you, David. So next question is from Galuh Yuliani from UBI. Okay, the questions. What is the strategy to teach multiple representation in science to various levels of students? I mean, the elementary, lower, and upper secondary, and university students.
Okay, I mean that's also a very good question. It is dependent on the knowledge of the students, and it's dependent on your understanding of the students. And just give you an example, I'm working with some colleagues in physics at the University of Western Australia. It's a grant that we're looking at how to introduce Einsteinian physics ideas into elementary and secondary school. And so in the elementary school and the lower secondary school, all this is dealing with like activities that are almost like games. And behind the activities is an understanding of what these phenomena might be. And then when you move to upper secondary and undergraduate, you can bring in much more detail in a more systematic manner. So I think this just goes back to all the earlier things that we learned in terms of like Piagetian learning. You're not going to introduce highly complex concepts to very young children unless it's extremely well scaffolded. Okay, thank you.
Okay, thank you. Move to the next question. It's from Agung Wijaya Subiantoro.
Oh, yes.
The question is how to analyze the coherency between knowledge and mass expressed by students.
Yeah. Thank you, Agung, and nice to see you, and thank you for your note. Right. So again, if I go back to that example I gave with the case study, and I had questions for students to show how they represented their understanding in terms of a written explanation, a diagram, a relationship between the variables, and whether or not this could be graphed. So if the students can say draw a diagram and make the text and it's consistent, then you got some level of coherency. If they're not able to put this together in a simple equation, then you know that they just do not know that. But if they put it together in an equation that's a wrong equation, then you know that you're lacking coherency there in terms of students understanding the relationship between the concepts that you put into an equation.
Mm-hmm.
Yeah. So if the students don't provide the information, it's very, very difficult, isn't it? Mm-hmm. To know whether they've got coherent knowledge. Thank you.
Okay, let's move to the next questions. It's from Abe from University of Lampung. The questions is from Abe from University of Lampung. Okay, the question is how to train students with appropriate strategies so that they can translate from one representation format to another correctly without leading to misconceptions.
Okay. How to translate the process. All right. I don't have a set answer here, but one of the points I would raise again, as I said before, let me go back to this notion of how you can refer to water. So if you want to indicate that water comprises molecules. These molecules are made up of atoms, And we cannot see these. We can only represent them in terms of models. So if we have a ball and stick model, the ball and stick model is there so that students understand that there's a relationship between the angles of these atoms that represent the molecule. And we can also show that there's some ionic aspect to this too. If we want to look at the space filling models, the space filling models are not showing any angles because they're actually the space filling model is created so that when the molecules are put together, they do have the angle, but it's actually hidden. So I think what we need to be doing is just be overt about what these different representations are doing, so students don't get misunderstandings. I don't know whether it's available to you, but I have very recently found some models where they are magnetic, and so, for example, you can you have space filling models of water, and you can only fit them together in a certain way, which represents the molecular interactions. So we have better and better models that are available to us. Mm-hmm. So I think the short answer is you have to be overt of what the representation is all about. If you're dealing just with text, what does the text tell us? And if we only have diagrams, what does the diagram tell us? And typically you've got to read two to understand. I hope that answers your question.
Okay, thank you, David. Let's move to the next question. Let's pick up a question from Ima Rosida from Universitas Negeri Malang.
Yeah.
Ima Rosida. Okay. The question is, can you please explain the difference between multiple representation and representational competence?
Yes, good question. So multiple representation is is all these different ways of presenting. So the way I presented this was multiple modes and multiple representation, but we can also, at a broader level, include modes and representation under one umbrella as representation. So the multiple representations can be different ways of presenting things, and the different ways they are created in terms of macro, submicro, and symbolic representations. Representational competence is how you use these representations to effectively explain the phenomenon. So a very competent individual will be able to use more of these modes and representations to explain the phenomenon under question. Yeah, thank you.
Okay, thank you, David. Let's move to the next question from a college from Philippine Normal University. Just pop up the questions. Is what are the key concepts of multiple representations?
I don't think you'd call them concepts. Multiple representations is a catch-all in a sense for how we represent what we're doing. I am talking to you. You are listening. Those are two representations. So within multiple representation, we can discuss any concept. So we can talk about homeostasis, and how do you deal with this in terms of conducting an experiment, talking about it, drawing about it, making relationships, so drawing diagrams, making relationships through a formula of some sort. So the concepts are within the multiple representations rather than the concepts of multiple representations. I hope that makes sense to you.
Okay, thank you. So let's go back to questions just down at the bottom.
Yeah.
From Nur Indah Sari from STKIP Pembangunan Indonesia Makassar. Right at the bottom.
This is right. How to develop multiple representations learning on HOTS students. I don't know what HOTS is.
High order thinking skills.
Oh, right. Okay, yes.
I think.
Okay. This is a key element that when I looked at that work of Sharon Ainsworth, she talks about the three aspects that the multiple representations can enhance coherence, they can be constraining, and they can lead to deeper understanding. So I think this fits into your higher order thinking skills, that if you can integrate the ideas from multiple representations, then you will develop higher order thinking skills. I think that's the issue.
Okay, thank you, David. We still have plenty of questions actually, but
keep going.
time does not allow us to continue. So we run out of time already. So we are very sorry, our audience, that we have to stop our sessions now. Thank you. So please give a big applause for our speakers today.
Yeah. Thank you. Very impressive number of questions. I'm sorry I couldn't answer them all or respond to them all.
So I give her time back to our MC. Thank you.
Well, thank you so much, Professor Treagust, for such an eye-opening presentation. And also thank you so much, Professor Ari, for moderating such a great discussion. Professor Treagust, as a token of appreciation, the organizing committee of the webinar would like to hand you a certificate, which will be virtually presented by our division head for international collaboration and university rankings, Bapak Haipan Salam PhD. So I'd like to invite Pak Haipan to virtually present the certificate to Professor David Treagust.
Thank you.
Okay. Good afternoon, Professor David Treagust. On behalf of Universitas Pendidikan Indonesia, I would like to thank for your insightful talks this afternoon. Thank you very much. Hopefully next year we can meet in Indonesia. Thank you.
Thank you. Oh, thank you. That's wonderful.
Thank you very much.
Thank you very much.
All right, and the next certificate will be directly handed still by Pak Haipan to our distinguished moderator for today's session, Professor Ari. So I'd like to again invite them both
for the certificate presentation. Pak Haipan and Prof. Ari, please.
Thank you.
Ladies and gentlemen, let's once again give a big round of applause for the talk on the multiple representations in science. David Treagust, chaired by Jake. Okay. So yeah, the certificate presentation marks the closing for today's webinar series.
Yes.
So I believe that this is the end of our session for today, and I have no information to share because this is the last out of 7 webinar series organized by DIA as a commemoration of UP's 67th anniversary or DS Natalis. So on behalf of the organizing committee of today's webinar series, I would like to again extend my sincere gratitude to everyone and my apologies for any inconvenience. So I am Ubad, your master of ceremony for today's event, signing off. See you in another event. Bye everybody, stay safe and stay healthy. Assalamualaikum warahmatullahi wabarakatuh.
Thank you.
Bye bye everyone.
Bye-bye.
Bye bye everyone. See you again next time.
Thank you.
Bye bye David.
Yeah, bye, Ari. Thank you.
Thank you very much, Dave.
Julie, thank you. Yeah.